Why do qubits collapse during measurement? Imagine trying to flip a coin that is spinning so fast you can't tell whether it's heads or tails. Now, picture that coin suddenly stopping and showing one side. That's similar to what happens when we measure a qubit. Before measurement, a qubit can be in a mix of both states, like being both heads and tails at once. This is called a superposition. It's a key part of quantum mechanics and allows quantum computers to do many calculations at the same time. When we measure a qubit, we are not just observing it like a classical object. Instead, we are interacting with it in a way that forces it to choose a specific state. This process is called wavefunction collapse. The wavefunction is a mathematical description of all the possible states a qubit can be in, along with their probabilities. When we measure, the wavefunction suddenly reduces to just one of those states, either 0 or 1. This happens because measurement in quantum mechanics is an active process. It involves an interaction between the qubit and the measuring device. This interaction extracts information from the qubit, which causes the superposition to break apart. The probability of the qubit collapsing into a particular state depends on the amplitude of that state in the wave function. For example, if a qubit is equally likely to be 0 or 1, measuring it gives a 50-50 chance of ending up in either state. The reason why measurement causes collapse is still a topic of debate among physicists. Some believe it is a fundamental part of quantum mechanics, called the Copenhagen interpretation. Others suggest that the universe splits into multiple outcomes, known as the many worlds interpretation, and the collapse is just an illusion. Regardless of the explanation, the practical effect is the same. The qubit ends up in a definite state that can be read and used. In quantum information theory, this collapse is very important. It turns the quantum information, which can be in superpositions and entangled states, into classical information that we can understand and process. But it also creates challenges. If a qubit collapses too early because of unwanted interactions with its environment, called decoherence, the quantum advantage is lost. That's why quantum computers need to be carefully isolated and protected from noise. In real quantum computers, measurement is used not only at the end to get results but also during calculations. It helps create entanglement and correct errors. The controlled collapse of qubits is a powerful tool that makes quantum technology possible. So, in simple terms, qubits collapse during measurement because the act of measuring forces them to pick a single, definite state from their many possibilities. This process is both a fundamental rule of quantum physics and a practical step for using quantum information in real-world applications.